First of all, I would like to thank everyone for coming today. I know it's a late in the day, and here is much later. Here is almost 8:30 in the evening. I would like to thank the Ambiental for the invitation, and in particular, Professor Jader, Silva Neto and Simone for inviting me to give this talk. And I would like to also thank Tammy for agreeing to come here at this time. So leaving her kid alone just for talking to us and talk a little bit about her research. So the talk today is about geothermal resources, so management of geothermal resources. And the specific topic of this talk is about a model, a reduced order model for managing geothermal resources. So before we start on the modeling aspects of this talk, I would like to give some motivation and some ideas of where it come from. Geothermal power energy is one of the topics that I'm completely passionate about. So it's about natural resources, a renewable natural resource that is related to the rain that percolates the soil, goes to the rocks until it reaches a reservoir, an area that is impermeable to other fluids, but at the same time, it receives heat from the core of the earth. So in some places in the world, in the whole world, the whole power generation, the whole electrical generation, the whole heating generation is through geothermal resources. When you look at the geothermal reservoir, and that's the name you call this area in which the fluid is located, there are a few phenomena there. So it's a very complex phenomenon. So there is a rain that percolates the soil, go to the rocks, and stay in the reservoir. There is the heat transfer from the core to the rock, and to the rock to the water, to the brine. There is a circulation, thermal circulation of these fluids within this reservoir, and there's a transport of fluids from the injection well and the production well. Why injection well and production well? Because industrial geothermal reservoir, they work with by injecting fluid, in this case brine. So brine is just a mixture between water and carbonates. So injecting brine into the reservoir, this brine get the heat from the rock, and this brine is produced in another well, and this brine can be either hot water or vapor, just steam vapor, or pure vapor, so just superheated vapor. So there are these three different cases. The production, although entirely renewable, so it's good for the environment, there is a big problem. Managing this is an issue because it's quite complex. Understanding how to manage these reservoirs, it requires us to understand first how the reservoir is generated, or how the reservoir, what's the geometry of the reservoir, and the properties, to the petrophysical properties of the reservoir. So it's important for modeling this reservoir to understand all these properties before going. And so this picture you see here, the right-hand side, is a synthetic picture. So it's not that the reservoir is just a hexahedron, but it has a very complex shape. The uncertainty associated to these properties, it's very high. It's very high because you're dealing here with a large distance. We talk here about 10 kilometers by 10 kilometers by 5 kilometers of depth. So you can imagine that it's quite difficult to get all these properties together. Just for give an idea, every single time someone drill to get samples of reservoir, either for oil and gas or for this, the cost associated with drilling and getting the samples is just around $500,000 or $400,000 per day of this operation. So it's quite expensive as well. So doing this is an expensive activity, but the reward as power is more than worth. So manage a reservoir means controlling the injection of brine, so it means mass flow rate and temperature, monitoring the pressure gradient between the injection and production. So this will determine how much fluid, how much brine will be produced, and how this brine will be transported across. So it's important to understand or to get detailed information of the reservoir itself. And when I say information here, means in particular permeability and porosity. The main issue, modeling flow in porous media is not a secret. It's been around for 20, 30, 40 years. But getting this in accurate way is extremely difficult because it is a very expensive, a competition expensive model. When we say here expensive model, we talk about an order of millions of cells, three-dimensional cells that need to be modeled and simulated. So usually there are four strategies for this. Either use high resolution, so a lot of elements there, high order accurate methods, so really accurate method for solving this, and high fidelity data, so a lot of data for probability and porosity distribution. But this approach is extremely expensive. So if you get a really supercomputer, you can get a very small area. You can get simulation for this very small area. Another approach is basically working on these three factors, either low resolution or lower the accuracy of the models, or getting less data. All of them, there will be a drawback, and there is no much way out of this. What you propose to do here on Tim's work is to integrate high order accurate methods with low fidelity data and a slightly low resolution method, but doing this in a very systematic way. So we get one of the best high order accurate methods that you can get for porous media flow, and a consistent and statistically sound ROM, reduced order models for the geophysical data. So this talk will be divided in two parts. So I will talk quickly about the numerical methods for the CFD point of view, or the computational multi-fluid dynamics point of view, CMFD, and Tammy will drive through the reduced order model. So in porous media flow, there are three equations that we need to solve. The Darcy equation, that's traditional Darcy equation in some way, in which the sigma term here is a merge between the probability, so this K here, the relative probability, so the ability of the fluid to go through the porous, saturation, viscosity. So this equation here is also called force balance, is actually balance the Darcy velocity, the U, and the pressure of the reservoir. So the whole movement inside the reservoir is controlled by this very simple equation. Looks very simple, but extremely difficult to calculate because the level of uncertainty about these two parameters here. The mass conservation, so it's very similar to any other mass conservation. Now you're conserving with respect to the saturation. And finally, the thermal energy equation, in which we have to pay particular attention to the interface heat transfer coefficient and the wall to fluid interface coefficient, and the source term, in this case here, the source of the reservoir. What is important, this method that we are using here, it's been tested against several other benchmark test cases, is that we use a dual mesh for the system. What does it mean? It means that you use a mix between a control volume method or finite volume method and a finite element method altogether. So all quantities that we seen on the equation before are basically determined in the finite elements, so this blue triangle here. So pressure and velocity are in this blue element, whereas the other quantities, so saturation, temperature, etc., are in these small hexes, which are control volumes. The advantage of this method that we get the best quality of finite element methods, which are extremely accurate and it's conserved mass. That's a quality from defined volume methods. At the same time, I would like to just highlight here that permeability is not just a value, but is assumed here as a tensor. So for every single element here, there will be a number of values for a tensor, because assuming here the tensor anisotropic. So now we're going to pass to Tammy, who will drive from now on. Tammy, and whenever you want, just let me know. I can move the slides.
Okay. Hi, everyone. Once again, my name is Temi Onimisi. I'm a PhD student in mechanical engineering, University of Aberdeen. I'm being supervised by the Professor Jefferson. In this section, I'll just quickly be talking on reduced order models. To start with, I'll give a brief introduction on reduced order models and then the description of the model setup that I'll be using, which is the non-negative proper orthogonal decomposition method, and then give a flow chart of how the model will look like. Next slide, please. So reduced order models are simplification of high dimensional system. They're actually used to approximate a high dimensional data set, a high dimensional system to a low dimensional space. And it's quite interesting because it ensures that all the essential features of the original space is being preserved. For petrophysical parameter, reduce other methods that are commonly used to reduce the degree of freedom are the upscaling methods. So for parameters for data sets like the permeability, porosity, the upscaling methods have been well studied and are used for reducing the dimension of the data. Basically, upscaling refers to the computation of effective coerced properties based on fine scale features from the high fidelity data, computing the low fidelity data sets from the high fidelity data. Next slide, please. In this work, we're actually concerned with projection based reduced order models. And so what we're interested in is projecting the high dimensional space to a low dimensional space spanned by some orthogonal basis. Now, the decomposition methods where this orthogonal basis can be obtained are depending on the nature of the data set that we want to analyze. If it's a bivariate data set, which is a two-dimensional data, your metrics, we could either use the singular value decomposition method, the SVD, or the proper orthogonal decomposition method, the POD. Now, for dimensions higher than 2, we use those are our tensors, 3D, 4D. We use our conical decomposition or the Tucker decomposition, hierarchical or Tucker train. So these are basically the methods that are used. But for this presentation, our focus is on two-dimensional data sets. So the method of choice here is the proper orthogonal decomposition method, which is the POD. Next slide, please. POD is a very powerful decomposition method that is used to obtain low dimensional approximate descriptions from high dimensional data sets. So if we're given a matrix X, POD seeks to factorize X in the form of equation 4. So POD factorizes it to give to U and V, where the columns of U are called the POD modes and the columns of V are called the POD coefficient. Now, what's quite unique is that the rank of U and V is much less, they are much less than the rank of V. So basically the dimensions of the matrix U and V, it's much less than the dimension of the matrix X. And we call our X bar the low rank approximations of the matrix X. The solution to equation 4 can actually be solved by just working on the optimization problem in equation 5. So solving equation 5, you're able to generate your U and V, which you use to produce your low rank approximations. Next slide, please. Now, a major drawback why we didn't use the pod model is because for upscaling petrophysical parameters like the permeability, porosity, it's expected that the output, the final result should be positive. However, for pod model, it's the pod modes are not constrained to be non-negative, so they could be negative or positive, and this is a drawback. So what we did was to add an additional constraint to the pod model, which is to enforce it to be non-negative, and so that the low rank approximations x bar will be greater than 0. Next slide, please. And so adding the non-negative constraint to equation 5, we were able to arrive at equation 6. Now, a major drawback of the combining non-negativity and orthogonality, which is U transpose U is equals to identity matrix, is that it makes the colon of U to be disjoint. So when you generate your U, you have a sort of sparse solution, and we don't want upscale permeability to be sparse, to be full of 0. So what we did is introduce an orthogonality distance measure, and then the resulting in equation 7. And so this is actually the minimization problem we are finally solving to obtain our U and V, which will generate our low rank approximations. Next slide, please. And so finally, the model that was built for the upscaling is the NPOD isoforce model, and it's a raw model that it's set up. So what we did was to combine the constraint pod, which is the non-negative pod method, with an interpolation method that is embedded within the flow simulator, the isoforce. The NPOD model is used to generate low rank approximations, and then the linear interpolation algorithm, which is embedded within the isoforce, is used to remap the low rank approximation to the coarse grid. If you remember in the previous slide when Jeff was talking, like the ideal setting to reduce computational burden, we want coarse grid, a high fidelity method, numerical method, and then with low fidelity data. So basically this is what we do. We have a low fidelity data generated as the low rank approximates from our NPOD model, and then we are remapping it using a linear interpolation method algorithm to the coarse grid. Next slide, please. So this is just a flow chart of the whole setup of the model. So we start giving our permeability, our data set. We determine the properties of the data set. We compute our NPOD model and evaluate our low rank approximate K-bar. We determine the properties of the low rank approximate, and then just in a kind of machine learning system, we just try to compare the results with the original metrics, with the original permeability data set. And once the whatever metrics we've set a metric that once it is acceptable, the result is outputted, and then we remap the low rank approximate K-bar to our simulation grid, run our simulation, and then stop and analyze our results. Next slide. So this section, I'll just be showing a benchmark of the model. We use it on an SP10 case 2 file. So the SP10 model is a known model, it's a reservoir model that has been proposed for benchmarking upscaling techniques in reservoir communities. And the model, although it's structurally simple, it's very heterogeneous, and it consists of 85 layers. Next slide, please. So for this work, we just extracted a layer, one of the 85 layers, to use as for our simulation, and it's layer 20. Next slide. For the simulation setup, the fluids are assumed incompressible. So the image here is showing the permeability distribution, and we have it in dimension of 6 by 11 of layer 20. This is the layer 20. So the fluids are assumed incompressible. The computational domain is initially saturated with fluid 2, and temperature ranging from 90 degrees to 150 degrees is near the injection well. The first boundary condition, there's no flux on the top and bottom surface, but fluids are allowed to leave the domain. Heat flux across both surfaces are 140. The second boundary condition is injection of pure displacing fluid at 10 raised to the power of -3 and 90 degrees Celsius. Next slide. So this is the setup for the simulation. Now the first step, like what I described in the flowchart, was to analyze our NPOD, analyze the low rank approximations before remapping it for simulation. So for the data set extracted from layer 20, the NPOD model was used to decompose the data set and generate low rank approximates. Now, as the number of modes increases, we can see that the information lost, the information loss reduces. So this graph is actually showing the information loss as number of mode increases. It's based on the Kullback-Leibler divergence statistics. And so we can see clearly that the information loss decreases and asymptotically tends to 0. Now the question is, at what ideal number of modes do we truncate to reconstruct our low rank approximations for simulation? Next slide, please. And so we used the statistics based on the cumulative variance. So we calculated the cumulative variance and set a bar. Once 99% of the variance is being explained, we truncate and choose those numbers of modes to use for our reconstruction. Now, based on these statistics, at 41 modes, 41 factors or modes, we have 99% of the variance is being explained. So for our low rank approximation, 41 modes was used for the reconstruction, and this is consistent with it validates with the statistics, with the Kullback-Leibler divergence statistics, which is significant and significantly acceptable. And also we have a minimum root mean square error. Next slide, please. And so after the statistics of our NPOD model we've been able to statistically say, yes, the using 41 number of modes will give us a very similar data to the original data set. Then the next thing is we went ahead to run the simulations. So this first simulation here is for the reference case. Actually, this is the high fidelity. This is for fine scale with the high fidelity data, and then you can see the saturation, the temp, and then the temperature, and then also the permeability distribution. Next slide. Okay, so this is the example of our upscaled case here. And this is actually using the low fidelity data with a coarse scale, in a coarse scale model. So we can see the permeability distribution here. Similarly, the saturation and then the temperature. Okay, the next slide, please. Okay, and this is for a very coarse scaled case. So just using 190 elements, although the result is not so good because it's really coerced and the result is kind of smeared, but it just gives us an idea that it's not the best of results anyway. And so these are results we've been able to get from the simulation using the reference case with the high fine scale model and high fidelity data, and similarly for the coarse case with low fidelity data sets. Please, next slide, just to summarize our results so far. Okay, so to show a comparison plot for the from the output, because we've seen the simulation files, the simulation the simulations for the find case, the reference case, and the coerce case. Now, just to show the comparison plot. So this is a plot comparing the production rates of fluid 2. Now we see the fine scale, which has 22,000 elements, and the high fidelity data was used, comparing it with the intermediate scale, which has approximately 4,500 elements. Here, the low fidelity data was used. We can see they're actually quite similar. It corresponds, just to show to show that our method is quite is it has quite potential. Yeah. But however, for the extremely coerced case where just 190 elements were used, the result is not so fine. It's a little smeared. It's different. This table here just gives a summary of the all what has gone. So, and we can see the CPU time. It's quite large. So used about 4 hours 82 minutes to run the reference case, and we just use 1 hour 51, that's in CPU time, to run for the coerce, the intermediate scale case, that's using our NPOD IC first model. You can see the time difference is quite large comparing it to the similar results that was gotten, just quite reducing the computational burden in terms of time and space too. Now, the volume of the data set for the reference case is a 60 by 220 data set. That's for the in the x direction, 60 by 20 in the y direction, because it's a tensor in k of x, k of y in different directions. Now, for the NPOD case, the data has been drastically reduced to a 60 by 41 diameter. That's the dimension of the data now, 60 by 41. And so for both case 1 and case 2, it's been reduced to 60 by 41, although the differences in case 1 and 2 is just the number of elements. So in case 1, it was 4,000, approximately 4,500 elements that were used. So I think just in summary, it's quite interesting because the NPOD model, it's interesting. We can see what has happened. It has similar results from the comparison plots, but the CPU time is drastically reduced. Next slide, please. And so just to conclude the final remarks. So advanced, we spoke about multi-scale and multi-physics models for their importance in design and optimization process, safety and environmental impact assessment on the whole geothermal reservoir system. Now, however, a major challenge that it's always there and has always been there is the uncertainty problem that's associated with you can't really get the right geophysical properties. And so you want to, as much as possible, make sure that the methods you're using to solve this, the flow models are, are quite high other methods, and fluidity was introduced here where we talk about a control volume finite element method for solving the multi-fluid flow problem, and it's based on a dual consistent pressure velocity representation in control volume and finite element spaces. And the focus is basically to numerical simulations on heterogeneous porous media using P1 DG P2 pair elements. Now, about the NPOD model. The NPOD model reduces the dimension of a large-scale data while enforcing non-negativity on the resulting low-rank approximations that are being reconstructed. And for upscaling, we've shown that the NPOD IC4 model, which was set up by just combining the NPOD model with an interpolation model embedded in the SFS IC4, performed quite interestingly well. And we are still working on more, just trying to adapt it to high dimensional data sets for now. I think that's all. Thank you, everyone. Any questions?
Thanks. Questions?
It takes some time for the students. May I?
See?
Okay, really nice talk. Jefferson and Temi, I do not work with finite element method, but I have seen some works. And there is a problem. When you look at the velocity, you have problems with the pressure. When you look at the pressure, you have problems with the velocity. You are working with saturation and temperature, as far as I understood, okay? I don't know if you have this type of problem. Usually, they have to do some sort of regularization to change a little bit the problem. And this looks very much with inverse problems that you have to use some regularization strategies. Please put the slide number 13. You see there, equation number 7, you are adding something there with a lambda, okay? How do you calculate the lambda? Temi, I believe that's for you.
Oh, okay, sorry, I was talking.
Jefferson is looking at you.
I didn't know I was on mute. Okay, so basically, lambda is set in such a way that as lambda increases, the orthogonality sort of reduces.
Mm-hmm.
And so you need to know what level of disjointedness you need.
Mm-hmm.
So there's actually, you could actually plot a graph to see the orthogonality of your reconstructed data as against your lambda.
Uh-huh.
Yeah.
Does that change a little bit your problem that you're looking at? Some sort of artificial way to solve because you're trying to improve something? Is that right or not?
Oh yes, so the way this is solved is just basically it's using the multiplicative update rule, this multiplicative, the Kern-Cohn-Touche conditions are used here to
Okay.
solve it. Yeah.
Okay. On slide number 15, you mentioned machine learning algorithm.
Yes.
Okay. Now it's a buzzword. So which one are you using?
So presently we are still optimized. The system is not fully optimized yet.
So
Okay.
let me just
Yeah.
say something here. So Temi and another student who is just handing his thesis last Friday. They both were working a similar problem, different approach, but similar problems. So Temi was doing is doing the pod, the reduced order model pod model. And the next stage of her work would be to replace part of the mesh-to-mesh interpolation that she's doing by a machine learning algorithm. So we are still investigating what is the best approach in this case.
Okay.
It's just because when you try to interpolate, so there are several methods for mesh-to-mesh interpolation. Most of them are quite expensive. So some of the method that Ken is using now is the simplest you can get for mesh-to-mesh interpolation. So there might be some issues there. We hope that by adding some sort of machine learning, so we don't have to decide which algorithm specifically we're going to use, but we're not going to be a classification algorithm. We hope that with this, it will improve the quality of the interpolation.
Okay.
Potentially to improve.
Okay. And a quick one. What is the effect of the boundary conditions? Did you apply boundary conditions, some sort of insulation or whatever, or not?
Yes. So what we have here, let me show here the slide. So what we have here, so this is a 2D representation of this layer.
Mm-hmm.
So we assume here there is a just for making sure that the simulation would be exciting to watch, because you can imagine that if you just inject 0.0001 meters per second of fluid, and you have to wait for 10 years to get something there, and it would be very boring. So what we did here, was to impose a Newman boundary conditions up and down. Okay, so just a heat flux boundary condition on that two surfaces. This value here is 100 times larger than it should supposed to be, and the value is usually 0.14 watts per meter square for reservoir. But again, if you keep this value, we have to wait a long time. So what I want to see is basically how the thermal diffusion would occur in the boundary layer. Remember that for a turbulent flow, there will be a huge mixing, but for a laminar flow or for a Darcy flow, this mixing will be very limited. So you have very hot region and a very cold region in the middle.
Okay.
So for the future, what we'll do is try to run the simulation for a real long time. We'll talk here about a few months of the numerical simulation itself.
All right.
But what we want here is actually just a proof of concept that our approach is working.
Okay. Thank you very much. Congratulations.
Questions?
Thank you, Tammy.
Questions, no?
If anyone wants to make a question in Portuguese, I'm happy to translate to Tammy.
Thanks, Jefferson. Thanks, Tammy.
Thank you, Simone. Thank you, everyone, for
Thank you.
attending and asking questions.
Thank you.